All right, physics reaction video number 66. Did a search for actually a whole bunch of stuff. I don't remember. Here we go.
All right, let's continue with our derivation of the work energy theorem. So we got to this point where the net work from...
Just going to pause and talk about, an extension of a set of slides, right? So she said, we got to this point. That's super cool, right? So obviously these annotations were maybe from the last time. And I think it's really great to be able to have a technology that helps you to sort of keep it going, right? Because if you're doing the old whiteboards or chalkboards, you erase it. Maybe you took a picture of it. So I just want to say that I love this derivation. I love it when we do it as vectors. There's actually... there's a couple of different ways to sort of make this last leap here. But I really love seeing it this way. This breakdown that she's about to do is super, super awesome. So this is, of course, one of the most famous things, although I wonder if I'm going to be able to say my usual stuff, which is that energy is made up. It's just an accounting trick, and that momentum is the whole story. We'll see. I get a lot of grief for that, but just pausing here to talk about being able to keep going where you left off.
A to B is equal to the integral of A to B, from A to B, of mvx dvx plus mv vy dy plus mvz dvz. Okay? And when we take that derivative, we will get 1/2 m all times the vx squared plus vy squared plus vz squared. And you'll take that from A to B. And in doing so, you see that this is going to just be the kinetic energy at point B minus the kinetic energy at point A.
Just wanted to pause here. So glorious, right? This is perfect, but this caught my eye up here. This equal sign drives mathematicians crazy, right? Is it this one? Yeah. What happened here? Well, this equal sign, it's like, oh, derivatives are fractions, trust me. And so we can just move this dt over here. It works. So I think that it's so fascinating, this sort of fake fight we have between physics teachers and math teachers, because math teachers, when I talk to my friends who are math professors, they get why we're doing this. They just say that, if in their class, they might spend a little bit of time of when that could break down, when that might be a problem, or they might structure this a little bit differently. And the physics folks are like, oh, it works so well. Look how we get to where I want to get to. I want to get to here so that I can do all of this stuff. And so I'm just always fascinated to see how people and students react to that, how math teachers react to that. Because this is the killer part. If soon as you can convince people of this one, all the rest is just turning the crank, and you get to this fantastic, look at this fantastic result. I just think that's super cool.
Okay, where these are going to depend on x, y, and z coordinates. Okay, so the work energy theorem states then that the net work done on a particle equals the change in the particle's kinetic energy. Okay, so this is our our work energy theorem.
Cool.
All right. So I want to quickly go over a problem-solving strategy, which is in the textbook as well. The first thing you want to do, and this is what I've been saying about a lot of the different force problems that we have, is to first draw a free body diagram for each force on the object. This helps you understand what's going on in the problem and proceed from there. Okay? Determine whether each force does work over displacement in the diagram. Okay? And make sure that you keep track of any positive or negative signs in the work being done.
Yeah, that's awesome.
Okay? Then you'll want to add up the total amount of work done by each force. Then set this total work equal to the change in kinetic energy and solve for any unknown parameter that you're looking for.
Cool.
Okay, you can also then check your answers, so basically making sure that it makes sense. Okay, and here's a few things to look out for. So if the object is traveling at a constant speed or zero acceleration, the total work should be zero and match the change in kinetic energy. Okay.
So I was just thinking about this one here, this 0, 1 here. So if something is going in uniform circular motion, it's constantly accelerating, but the kinetic energy doesn't change. Okay. So yeah, there's a subtlety here, right? So it's actually two different types of acceleration, right? There's acceleration that turns you and acceleration that changes your speed. And so here, of course, she's talking about the type of acceleration that changes speed. And notice that this is a sort of a non-directional word here. And so she's really talking about sort of the non-directional version of acceleration. But it's always these subtle things, right? So you know that in this class at some point they're going to be doing uniform circular motion and it's going to come back around again. But I love how this non-directional word, so instead of saying velocity, she said speed, sort of connects to the sort of scalar version of acceleration, the speed up, slow down version of acceleration. Let's see if that same subtlety is in the next two. Right, so same thing, right? Sped up, slowed down. These are non-directional, right? So that's really, really interesting.
If the total work is positive, the object must have sped up or increased in kinetic energy. If the total work is negative, the object must have slowed down or decreased in kinetic energy. Okay, so this makes sense since work is equal to KB minus K sub A, right? So if this is positive, okay, this change in kinetic energy must have been positive.
Cool, that's super awesome.
Okay, if the total work is negative, that means the change in kinetic energy must have also been negative.
This is a really great example of the power of video, right? So just take a look at this. This kind of looks weird if you just look at this, like plus, plus, minus, minus, what? Right? But if you watch the video and you hear what she's talking about, it's like totally nailing these three, or I guess these last two, bullet points here. And so the power of video and the ability of students to rewind and say, what the heck's going on is fantastic compared to a fixed slide or sheet of paper or handout, because this just kind of looks funny, right? If you just look at it. And so I really, really am so impressed by the dynamic nature of, I guess, video, or I guess being live in front of somebody. What's interesting, of course, is let's say that you've got students watching this video or you did this live and their notes look like this, right? Well, if their notes look like this, they have to somehow tie it to the fact that they're commenting on these bullet points. So I think that for me, it's like working with students like, okay, well, I might pause and say, okay, you guys, you probably have this written in your notes now. What are you going to do a week from now when you're studying for the exam and you see this? And I would encourage my students to maybe draw tiny little arrows or write the word sign or something, right? Because otherwise they come a week later and they're like, well, I don't get this. So I think that idea of helping students really have their notes be as useful as possible is really interesting.
Okay, we have to balance our equation. So these things must make sense, okay, in your problems. So let's go ahead and do an example together. This is 7.10.
Cool.
It states that a bullet has a mass of 40 grains, or we're going to say 2.6 grams.
All right, 2.6 grams. All right, I got my empty can of Coke here. So this is 355 grams. Oh my gosh. So what? 100 bullets would weigh less than a full can of Coke? 100 bullets. This seems a little light. Man, I don't know anything about bullets. I don't I don't know if 2.6 grams. I'm thinking that's a wimpy bullet. I don't know. Muzzle velocity 335 meters per second. Woof, that's fast, right? Speed of sound. Okay, so yeah, this should penetrate. 8 1-inch pine. Oh my gosh. Yeah, this bullet's cruising. 8 1-inch pine boards. By the way, take a look at Smarter Every Day's video of supersonic baseball. Yeah, don't try to catch a supersonic baseball. Okay, and then each one 1-inch. 8 1-inch pine boards, each with thickness of 0.25 inches. 7.5 inches. Okay, that's weird. I think that means that they're called 1 inch, but they're actually 3/4 of an inch, because it's not like this dimension is an inch, right? Because they're saying that this here is 0.75. There's no way this is 1. So I don't know why they're called 1-inch pine boards. Okay, so a pretty light bullet going really, really fast. Penetrates whatever 8 times 3/4 is. What's that? Yeah, 6 inches in. Wow, it seemed that. Whew, that's a fast bullet.
And a muzzle velocity of 335 meters per second. It can penetrate 8 1-inch pine boards, each with a thickness of 0.75 inches. What is the average stopping force exerted by the wood as shown in this figure? Okay, so we need to determine the stopping force exerted by the wood. So this is going to come back to our frictional force. Okay. Okay, so the first step is going to be to use our knowledge of our work energy theorem, which we just defined as our work is equal to K at point B, or we can, excuse me, say our final minus our K at point A, which would be our initial.
Cool.
Okay. And I mentioned that we need to take into account our friction or our stopping force. Okay, so that would be equal to negative F, I'll say sub S for stopping, multiplied by our distance. So I'll say delta X. Okay, so we'll say that this is the positive X direction. Okay. So
I mean, that sign is so interesting, right? So if you get that sign wrong, or you're lazy with it, or you call it F dot X, which is, or F dot R, which is, I think, what was on 3 slides ago. Ultimately, you're going to get a force, right? If you didn't put a negative sign there, your force would have been negative. So what makes more sense, to say that the force of the board is negative, or that the force is just pointed in the other direction? I mean, you're going to grab your calculator, you're going to get whatever the answer here is going to be. And so I'm really intrigued by putting the negative sign in right here and say, look, I already know that the force has to be acting in the opposite direction of X. In fact, she even said here's the positive direction. So this is built so that this is going to give us a positive answer. I think that's probably how I would do it too, but I guess I'm just saying that it seems reasonable to just kind of let the negative signs go for a while, finish with an answer, and then say something about how, oh boy, I wonder which way that was acting. Oh, it must have been acting this way. So I think that's really interesting.
Our delta X will be our thickness of the boards. Okay, so our thickness is 8 times 0.75 inches, and we need to get that into meters since our velocity is in meters. So let's go ahead and convert inches to centimeters. So that would be 2.54 centimeters per inch. And then we have, per each meter, we have 100 centimeters. Okay, so delta X then is going to be
15 centimeters?
0.152 meters.
Yep.
Okay. Now, from our equation here, we also need to evaluate this portion here. So we're stating that the bullet passes through all of these and then stops at the very end. Okay, so we can assume that our kinetic energy at the final position is 0. So we are saying that it lost all of its kinetic energy through the boards. Okay, so our kinetic energy final is 0.
So I just paused and smiled there. There's some sort of noise in the background, right? And so I'm always fascinated as I watch these. There's some people who you can tell there's a pause in the video when the background noise mysteriously disappears. There's people who just say, "Hey, cut it out! I'm doing something." There's other people who just sort of plow through. And I think that our society is really sort of getting used to it, right? We're just used to it. Just let's keep on trucking here. So, I mean, I only just happened to notice it sounded like maybe a ruler slapped onto a board or something. And who knows what's going on? But I got to say, it doesn't really bother me. I noticed it, yeah, because I'm here and I am talking about it, but I don't think it changed the flow of the work here. A couple of things here. Significant figures. Love the fact that there's only 2 here, there's 3 here, and only 2 here, and 3 here, and 1 there, right? I mean, it's all over the map. So I love that because I hate significant figures. I really, really loved this. I mean, come on, you just got to keep on doing this with your students, right? If they're not good at this, right, you just got to do it over and over and over again until they can really get good at this. And then, 15 centimeters, what is that? Yeah, that's about 6 inches. So this is holding together.
Okay, so then what we'll do is we will put these into our equation here. Okay, so this is, I'll just say 1. Okay, and we will say it is 0. I'll start on this side. We have negative f sub s delta x equals 0 minus k sub I. Okay, and we'll rearrange that to equal the stopping force, since that's what we're looking for. So and that'll be equal to k sub I over delta x, or 1/2 mv sub I squared over delta x.
Cool.
Okay, and then all we have to do is plug everything in. So we have f sub s equals 1/2 times our mass, which is 2.6 grams. We want that to be in kilograms, so there are 1,000 grams in 1 kilogram. Okay, so for this guy, we'll say that we have 2.6 grams times 1 kilogram over 1,000 grams.
Nice.
Okay, can do that real quick. 2.6 over 1,000.
Love that.
Yeah,
I love showing that you gotta grab our
0.0026
calculators.
kilograms. Okay,
awesome.
so we can plug that in down here. 0.0026
so
kilograms.
6 times 3.
And you could have left it in a fraction here, it doesn't really matter. And then multiplied by our velocity, which is 335 meters per second squared. Okay, and then divided by our displacement, which is 0.152 meters. Okay, so let's go ahead and do that calculation real quick.
1,000 to 2,000, I'm saying.
And you'll get a stopping force of 960 newtons.
Wow. Whew.
So this is our stopping force.
Wow, 96 G's.
Of that, of the wood. The stopping force exerted by the wood. Okay?
All right, just gonna stop there. Very, very cool. Really loved a lot of features to this. Loved the signs, like being consistent with the signs, and then so okay, we can get it done. I loved just the consistency of the unit conversions, right? I mean, students have to see that. I think it's a really interesting problem. I gotta say, this 1-inch pine board's thickness of 0.75 inches is really throwing me off. Why do they do that? Another question I have is, what happens if you space them, right? Like, what if there's a gap? Would you still have the same penetration? I actually don't know. My guess is there's some extra surface stuff. Like breaking the surface is maybe a little harder than going through the bulk. I don't know. That's an interesting question. And I really, really loved the beginning stuff, that integral, the linchpin to all of this. I thought that was really great. All right, everybody, have a great day, and remember, physics teachers are awesome.